Fine, let's start. There's a star in the shoulder of Orion that has been watched by every civilization that ever looked up. It's one of the brightest things in the night sky. You've seen it without knowing you've seen it. Reddish, steady, ancient looking. Except it isn't steady, and it isn't behaving the way it used to. And the people who spend their careers watching it are having arguments they can't resolve. These are 10 of those things. Number 10. The runaway with a dead sibling. Betelgeuse is moving, not slowly, not gently. It's hurtling through the galaxy at 30 kilometers per second, roughly 108,000 kilometers per hour, and it's doing it alone, far from any cluster of stars it might have grown up near. We call stars like this runaways, and when you trace Betelgeuse's path backward through space, trying to find where it came from, something strange happens. The trajectory doesn't cleanly lead anywhere. It doesn't point back to a known stellar nursery the way it should. The math keeps coming up empty. The leading hypothesis is quietly unsettling. Astronomers think Betelgeuse was originally part of a binary system, two massive stars born together, orbiting each other. And then one of them exploded, a supernova. The shockwave from that explosion kicked Betelgeuse loose, sent it tumbling out of its birthplace at speed, and left it wandering ever since. There may already be a dead star somewhere in Betelgeuse's past, a cautionary tale it has been running from for millions of years, and the fact that we can't cleanly trace its origin suggests its path may have been altered more than once, possibly by more than one event. As it moves, Betelgeuse plows through the surrounding gas and dust of the interstellar medium, and that collision creates what astronomers call a bow shock, a massive compressed wave wrapping around the front of the star the way water piles up in front of a moving boat. The Herschel Space Observatory confirmed it in January of 2013. That bow shock is more than 4 light-years wide. 4 light-years, the entire distance from Earth to the nearest star system, as a wave, pushed by one star's motion through space. Betelgeuse has been leaving a mark on the galaxy itself for a very long time. And wherever it came from, whatever happened to its sibling, it has been carrying that history with it ever since. Number 9. The oldest record of this star just became obsolete. For at least 65,000 years, the Kokatha people of Australia's Great Victoria Desert have been watching the sky. Their oral traditions, stories encoded carefully and passed down with precision through generations, describe a character called Nyaruna, a hunter in the stars, with a club of fire magic in his right hand. That club is Betelgeuse. And the story doesn't just name the star, it encodes its behavior. The fire magic in the club charges up and releases, charges and releases on a repeating cycle. That cycle corresponds almost exactly to Betelgeuse's roughly 400-day pulsation, the regular brightening and dimming that Western astronomers didn't formally document until the 1800s. Dr. Dwayne Hamaker at Monash University documented these traditions in 2017 and identified them as the only known descriptions of pulsating variable stars in any indigenous oral tradition in the world. The Kokatha people were tracking this star's rhythm before Europeans had written language, before telescopes existed, before most of what we think of as recorded history. The 400-day rhythm, stable across the full span of human memory, across every generation that ever told that story, is now gone. Since the events of 2019 and 2020, Betelgeuse has not been running on its ancient cycle. The fire magic in the club, the heartbeat that anchored a story told for possibly tens of thousands of years, no longer behaves the way it did. Something changed that no human being, in any culture, in any recorded or oral period of history, has ever observed before. We are, in the most literal sense, in new territory with this star. Number 8. 2,000 years ago, it was a different color. Around 100 years before the Common Era, a Chinese court astronomer named Sima Qian looked up at the star in Orion's shoulder and described it as yellow. About a century later, a Roman scholar named Gaius Julius Hyginus, personal librarian to Emperor Augustus, compared the same star to Saturn in color. Yellow-orange. Like old brass, not red, not even remotely red. Professor Ralph Neuhauser at the University of Jena pieced this together in 2022, cross-referencing Chinese, Roman, and Greek astronomical texts with enough rigor that the statistical confidence came out at 5.1 sigma. The same threshold physicists use to confirm the discovery of a new particle. This wasn't a hunch. It was a measurement. But the most compelling piece of evidence isn't what ancient astronomers said about Betelgeuse. It's what they didn't say. Claudius Ptolemy, writing in the 2nd century of the Common Era, compiled a careful catalog of red stars visible to the naked eye. He listed Antares, he listed Aldebaran. Both are unmistakably red, both comparable to Betelgeuse by any modern measurement. Betelgeuse isn't on the list. One of the 10 brightest objects in the night sky, a star Ptolemy certainly knew about, and he did not classify it as red, because at the time he wrote, it wasn't. By the 1600s, Tycho Brahe, perhaps the most meticulous naked eye observer in history, noted that Betelgeuse was redder than Aldebaran. By now, it rivals Antares. The transition from yellow-orange to red marks a specific and meaningful moment in a star's evolution. It signals that the star has recently entered its red supergiant phase, the last phase, the phase that ends in a supernova. And in stellar terms, Betelgeuse got there fast. This transformation happened in roughly 2,000 years, which is considered rapid for a star. The color we see tonight in the shoulder of Orion is geologically recent. The star we're watching changed within recorded human memory. And it is already doing things no previous generation ever saw it do. Number 7. The companion nobody found for 100 years. For nearly a century, astronomers had a nagging feeling about Betelgeuse. The star has a long brightness cycle of roughly 2,100 days, about 5 3/4 years, that never quite fit the standard models for a single pulsating star. Something was driving it. Some external influence. 2 independent research teams examined decades of photometric and spectroscopic data in 2024, and both reached the same conclusion. Betelgeuse almost certainly has a companion star, an unseen object orbiting it, periodically plowing through the surrounding dust and clearing a path, making Betelgeuse appear to brighten on that long cycle as the dust clears from the line of sight. On July 21st, 2025, a team led by NASA senior research scientist Steve Howell confirmed it. Using a speckle imaging instrument called ALOPEC on the Gemini North Telescope atop Mauna Kea in Hawaii, they directly detected the companion for the first time. They named it Siwarha, a feminine Arabic name linked to the tradition of Orion, a star that had been theorized for nearly a century, hiding in the overwhelming glow of a supergiant, finally seen. Now here is where this gets genuinely strange. Siwarha doesn't orbit Betelgeuse from a comfortable distance. It orbits inside Betelgeuse's extended outer atmosphere. Betelgeuse is so enormous that its outer envelope, the diffuse extended halo of gas and material surrounding it, reaches far enough into space that another star fits inside it. Siwarha orbits within that envelope like a marble inside a soap bubble. It has been doing this the whole time, hiding in plain sight inside the star it orbits. When Betelgeuse explodes, Siwarha will not survive. 2 stars, 1 death. And the quieter implication is this. Some of the readings that looked like warning signs over the decades, the anomalous long-period brightness patterns, the data that didn't fit single-star models, were just this hidden star doing its quiet orbit, sweeping dust aside. The warnings were real. They were just telling us about something we didn't yet know existed. Number 6. The boiling inside. It is on a scale we don't have good words for. If Betelgeuse sat at the center of our solar system, its surface would extend past the orbit of Mars. The star's diameter is roughly 750 times the diameter of the Sun. You could fit approximately 300 million Earths inside it by volume. These numbers eventually stop meaning anything. So here's the frame that actually lands. It is incomprehensibly large, and the entire thing is boiling. In 2009, the ESO's VLTI Amber instrument resolved Betelgeuse's atmosphere with enough precision to see the internal motion. What they found were convection cells, rising blobs of superheated plasma, that are individually as large as the entire star. Not a fraction of the star, not a region of it. Each individual bubble, rising and falling at supersonic velocities, is comparable in size to Betelgeuse's full radius. The Sun has millions of small, fine convection cells working in concert across its surface, like a pot of gently simmering water. Betelgeuse has a handful of enormous chaotic ones, each the size of the whole thing, churning the star from the inside with no apparent coordination. And then there are the shells. 6 distinct atmospheric layers have been mapped around Betelgeuse, extending hundreds of astronomical units into space. Rings of expelled gas and dust, each one a record of a previous violent episode. They are layers of the star's own former self, drifting slowly outward. A physical archive, written in expelled material, of every major convulsive event Betelgeuse has had across the last several thousand years. The star has been erupting, in various ways, for a long time. We just recently got the instruments capable of reading the record it left behind. Number 5. It blew its own surface off. Nothing has ever done that. In the autumn of 2019, Betelgeuse started to dim. By February of 2020, it had reached its faintest level in almost 200 years of recorded observation, 2.5 times dimmer than its usual minimum. Amateur astronomers noticed. Professional astronomers with serious instruments noticed considerably more. There was a brief but genuine collective moment across both the scientific community and the general public of, is this actually it? The explanation, when it finally came together, was in some ways more alarming than a simple pre-supernova event would have been. A convective plume, a bubble of superheated material more than 1 million kilometers across, had forced its way up from deep inside the star, generated shocks as it traveled, and blasted a chunk of the photosphere into space. The photosphere, the actual visible surface of the star, not gas from the outer atmosphere, the surface itself, gone, ejected. The mass of that ejected piece was several times the mass of our moon. The most powerful solar storms the sun ever produces, the coronal mass ejections that occasionally disrupt satellites and power grids here on Earth, are roughly 400 billion times less massive than what Betelgeuse threw off in 2019. 400 billion. NASA was unambiguous in its summary. This is something never before seen in a normal star's behavior. The ejected material cooled as it traveled outward, condensed into a cloud of dust, positioned itself between Betelgeuse and Earth, and blocked enough of the star's light to produce the dimming event observers recorded. By 2022, Hubble observations confirmed the outer layers had largely recovered. The dust was dissipating. The star looked, from the outside, more or less fine, but the same spectra that showed recovery also contained this description of the surface: bouncing like a plate of gelatin dessert as the photosphere rebuilds itself. The outside healed. The inside was still sloshing. Those are two meaningfully different things, and it's worth holding that distinction clearly. Number 4. Its heartbeat broke. The deadline to fix. It is now. For at least 200 years, Betelgeuse had a rhythm. Every roughly 400 days, it brightened, then dimmed, then brightened again. Consistent enough that observers in the early 1800s could track it by eye and confirm the period. It was, whatever else was unpredictable about Betelgeuse, the one thing you could count on. After the Great Dimming, that rhythm halved. The 400-day fundamental pulsation mode was replaced by a dominant cycle of around 200 days. The star was now oscillating twice as fast. And Andrea Dupree, the astrophysicist at the Harvard-Smithsonian Center for Astrophysics, who has spent more time studying Betelgeuse than perhaps anyone else on the planet, stated it plainly. For 200 years, it had a nice 400-day oscillation in brightness. But that's gone now. The working explanation from Morgan McLeod's team at Harvard is that the surface mass ejection disrupted the internal pulsation mode, like striking a bell and then pressing your finger against it, canceling the resonance and allowing a different frequency to take over. Their prediction was specific. The old 400-day rhythm would reassert itself within 5 to 10 years of the dimming event in 2020. That window is closing. We are inside it right now. A separate team at Cochin University characterized what happened not as a temporary disruption, but as a dynamical transition, causing a permanent change in the pulsation dynamics of the star. Not the old bell ringing down. A new bell entirely. Then, in early 2023, the inner atmospheric layers showed what later analysis identified as the second strongest expansion ever recorded in Betelgeuse's atmosphere. Something large moved inside the star again. And in the months that followed, the external brightness went quiet, flatlined, no significant variations, while underneath, the temperature and radial velocity continued in full disorder. The surface went still. The interior kept boiling. A star that had gone externally calm while remaining internally chaotic, and the researchers who noticed that detail found it difficult to file away neatly. We are still watching. We are still waiting for the old rhythm to come back. The deadline the scientists set for that recovery is now. Number 3. We have been measuring the distance wrong. For most of modern observational astronomy, the accepted distance to Betelgeuse ranged somewhere between 642 and 725 light-years, depending on which method you used and which paper you trusted. That spread existed because measuring stellar distances is genuinely hard, and Betelgeuse, variable, extended, complicated, gave different answers to different techniques. In 2020, Dr. Meredith Joyce and colleagues published a careful reanalysis using asterosismology, the study of how vibrations travel through a star's interior, the same principle geologists use to map Earth's interior using seismic waves. Combined with hydrodynamic modeling through a code called MESA, their result came out at roughly 530 light-years, 25% closer than we thought. That is not a rounding error. That is not within the margin of uncertainty. That is a significant revision to the distance of one of the most studied stars in the sky, and it changes the picture of what a Betelgeuse supernova looks like from here. At that distance, when it goes, it will shine at roughly the brightness of a quarter moon, but concentrated into a single point, not spread across the sky. A dot. One impossibly bright dot, visible in daylight, bright enough at night to cast a clear shadow on the ground. For weeks, possibly months, every person on Earth will see it, whether they're looking for it or not. But here's the thing. Joyce's own team used the closer distance to argue that the star has more time, not less, because the revised distance also implies a physically smaller star. A slightly smaller Betelgeuse sits at a slightly earlier stage of its evolution. The number that alarmed people was immediately turned around and used as a reason to be calm. The same data point, two completely opposite conclusions, both mathematically defensible from the same measurement. That's the pattern with Betelgeuse. Every alarming finding carries its own counter-argument built in. The star keeps handing you a reason to worry, and a reason not to, sometimes in the same sentence. The scientists keep arguing. The star keeps burning and doesn't weigh in. Number 2. Humanity built a tripwire. It has been armed since 2009. Somewhere under the South Pole, buried in Antarctic ice at depths between 1,500 and 2,500 meters, there is a cubic kilometer of instrumented glacier. 5,160 sensors, each one waiting for the faint flash of blue light that occurs when a neutrino, a particle so weakly interacting that it can pass through the entire mass of the Earth as if the planet simply isn't there, occasionally collides with a water molecule in the ice and produces a detectable signal. This is IceCube, and since 2009, it has been running continuously, sending data in real time to a global network called the Supernova Early Warning System. SNOOZE 2.0. Here is what SNOOZE is built to do. When a massive star's core collapses, it produces an enormous burst of neutrinos, carrying nearly all of the energy of the explosion in the first 10 seconds. These particles barely interact with anything, so they travel outward through the collapsing star at nearly the speed of light without slowing down. The actual explosion, the visible blast, the shock wave, the light, has to fight its way through the dense outer layers of the dying star. That process takes hours. The neutrinos arrive here first, hours before the sky changes, hours before any telescope picks up anything unusual in Orion. SNOOZE is designed to catch that neutrino burst simultaneously across multiple detectors, recognize the signature, and automatically send alerts to every major observatory on Earth, so that instruments are already pointing at the right part of the sky before the first photons from the explosion ever reach us. Betelgeuse is close enough that pre-collapse neutrinos, emitted during the accelerated nuclear burning in the final phase, before the core gives way, might be detectable even before the explosion technically begins. The system could flag what's happening inside the star, while the star still looks normal from the outside. There are roughly 40 stars in our region of the galaxy currently in a supernova-ready state, already red supergiants, already in the late stages of their lives. Betelgeuse is the most prominent among them. SNOOZE wasn't built for any single star, but everyone involved knows which star sits at the top of the list. The infrastructure to detect the death of Betelgeuse before a single photon of it reaches your eye is already built, already running, and already watching. Tonight. Right now, while you are sitting wherever you are sitting. If the alert fires, telescopes around the world will pivot toward Orion's shoulder. A few hours after that, a point of light will appear that wasn't there before, and it will grow brighter and brighter and brighter over the hours and days that follow. The tripwire is armed. It has been armed for 16 years. The question is purely when. Number 1, we cannot tell what's burning in its core, and that is everything. Here is the thing at the center of all of this. Everything covered so far. The ejected surface, the broken pulsation, the hidden companion, the ancient color change, the runaway trajectory. All of it is in some form observable. We can point instruments at Betelgeuse and receive data. We can argue about what the data means, and we do, constantly. But we have data. What we cannot see from any distance with any instrument currently available to science is what element Betelgeuse is fusing in its core right now. Massive stars burn through a sequence of fuels over their lives. Hydrogen becomes helium. Helium becomes carbon and oxygen. Carbon becomes neon, then sodium, then magnesium. Each stage runs shorter than the last. Hydrogen burning lasts millions of years. Helium burning, hundreds of thousands. Carbon burning, roughly 1,000 years. And when the core eventually fills with iron, the absolute dead end of stellar fusion, the one element where the process stops releasing energy and starts consuming it, the core collapses in less than a second. What follows is a supernova. The debate that has been running in the scientific literature since at least 2023 is whether Betelgeuse is currently burning helium or carbon in its core. If it's burning helium, the mainstream estimate puts the explosion somewhere between 10,000 and 100,000 years away. That is the position held by most active researchers on this star, including Morgan McLeod at Harvard and Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics. If it is in late-stage carbon burning, as Dr. Hideyuki Sayo at Tohoku University in Japan argued in a 2023 paper in the monthly notices of the Royal Astronomical Society, based on analysis of Betelgeuse's 4 distinct pulsation periods, then the core could collapse within a few hundred years. The language in that paper was specific. The core will collapse a few tens of years after carbon exhaustion. Dr. Meredith Joyce's team responded immediately. Wrong radius assumption. Helium burning. 100,000 years. Calm down. Their rebuttal was published in the research notes of the American Astronomical Society. And then, in the middle of this argument, both sides arrived at the same sentence. It appears in Sayo's paper, and neither team disputes it. It is not possible to determine the exact evolutionary stage, because surface conditions hardly change in the late stage, close to the carbon exhaustion and beyond. Read that carefully. The surface of a star that has 1,000 years left looks the same from the outside as the surface of a star that has 100,000 years left. Carbon burning lasts approximately 1,000 years in a star of Betelgeuse's mass. If Betelgeuse is in the late stage of that phase, which Sayo's team believes it is, then the window in which the explosion could occur is already open, has been open, and no brightness measurement, no spectral analysis, no pulsation study can close it. Joyce said it directly, in plain language, in an email to journalists. If it were easy to tell whether a star is undergoing helium or carbon burning simply by observation, we could stop arguing. They have not stopped arguing. So here is where we actually stand with this star. There is an object 530 light-years away that has physically thrown its own surface into space, lost a 200-year-old heartbeat, hidden a companion star inside itself for a century, turned red within recorded human memory, and is currently being monitored by machines buried in Antarctic ice that are designed to alert us before its death becomes visible. And the one question that matters most, how much time is left, we cannot answer. Not because we haven't tried, because the universe doesn't put a label on the outside of a dying star. The surface conditions don't betray it. The color stays steady. The light keeps traveling toward us. And somewhere inside, in a core we can never directly observe from here, something is burning. And when it stops, it will stop in less than a second. The only warning will come from machines, not from the star itself. Not from a brightening, not from a change in color, not from anything visible. A flood of neutrinos will pass through the planet, through the ground you're standing on, through the chair you're sitting in, through you, detected only by sensors buried under kilometers of ice at the bottom of the world. That signal will go out. Telescopes will turn. And a few hours after that, you'll look up at Orion, and something will be different. A point of light in the hunter's shoulder that wasn't there the night before. We might see that in our lifetimes. Our children might. It might be 10,000 years from now, and every generation between here and there will go to sleep under the same red star and wake up under it again, and it will look exactly as it does tonight. The star doesn't know we built the tripwire. It doesn't know we've been watching it for 65,000 years, encoding its rhythm into stories, cross-referencing its ancient color in court records from China and Rome, burying sensors in Antarctic ice in anticipation of its death. It's just burning 530 light-years away, on whatever schedule it's keeping, in whatever phase it's in. And the honest answer to the question this video is built around is, we don't know, and we can't know. And there's something quietly profound about that. About the fact that one of the most studied, most watched, most documented objects in human history is still capable of keeping its most important secret from us. It has been in the sky for every human life ever lived. It will probably be there tomorrow. Probably. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.